Okay, so continuing with our discussion of gas laws here, a couple other related issues. So similar approach to solving problems, but a couple other things that may pop up that you should be aware of. You run into while you're solving problems. One here is this abbreviation STP. STP here stands for standard temperature and pressure, as I have it written out here. The standard pressure for studying gases is 1 atmosphere, right? So like we said, that's pretty close to the pressure outside, particularly if you're near sea level. So that's usually the external pressure when you're studying a gas. The standard temperature for studying a gas is 0 degrees Celsius or 273 Kelvin. And that's because in a laboratory setting, that is the easiest temperature to maintain because that's where ice melts. So if you jacket a vessel in which you're studying gases with something like ice water, any heat that comes out of your gas will get absorbed into the ice water, maintain the heat will go to melting the ice, and it'll keep your temperature at 0 degrees C. So that's the important one to remember is 273 Kelvin is standard temperature. Now, there's actually a physical relationship that is helpful when you're talking about STP, and this can be particularly helpful. So you've got to know what STP means. If it comes up in a problem, you need to know what pressure and volume to use. But there's another relationship that goes along with STP that can be really helpful in a problem, and that is called the molar volume of a gas. So we're actually going to solve for it here, but this is a pretty common number that will often be useful in problems. What volume does 1 mole of gas occupy if it's at standard temperature and pressure, or STP? So what we want to do here is solve volume per mole. So if I take PV equals nRT, right, and we know V is volume and N is mole. So if I keep V on top but I divide through by N, I can get the volume per mole. Right? And if I move P over to the right side of the equation, just divide both sides by P, that would be RT over P. So the relationship between volume and mole, or V over N, would be the gas constant, 0.0821 liter atmospheres per Kelvin mole, right, times the temperature, right, at STP, that's 273 K, right, and divided by the pressure, which standard pressure exactly 1 atmosphere, so it's not a one significant figure value there, it's exact for STP. So really this is just R times 273. Right, and this comes out to 22.4. So 22.4 liters corresponds to 1 mole of gas if you're at STP. Right? So if you notice in a problem that it tells you the gas is at STP, this is sort of a shortcut you can take to solve the problem if you remember this relationship, this 22.4. Now 22.4, that's about the size of a beach ball. So maybe a little smaller than a standard beach ball, but if you're at 0 degrees C, you're probably not playing with a beach ball too often at 0 degrees C, but 1 mole of gas would be about that size of a beach ball. Now, let's look at that in the context of a problem here, because like I said, you do need to know what STP is to solve this problem, but you can actually maybe take a little shortcut if you know this 22.4. So we've got a sample of nitrogen gas. We're given a volume, a temperature, and a pressure. Right? And we want to calculate what is the volume at STP. Now, we could certainly tackle this as a change of circumstances problem. So if it's STP, that means the volume has changed. Then that's what we're solving for. The pressure has changed because it went from 745 to 1 atmosphere, which would be 760, right? And the temperature has changed because it would go from 30 to 0 Celsius, appropriately when we change that to Kelvin. So that's one way we could solve this problem, is combine gas law. P1 V1 over T1 equals P2 V2 over T2. That would work. But if we notice the STP here, we might recognize that if we can figure out how many moles are in the sample, we can relate that directly to the volume that we're looking for, if we remember that 22.4. So if I just take the first two pieces of information and solve for moles, I can use the molar volume as sort of a shortcut for the second part of the problem. So if I just take PV equals nRT, and again I'm solving for N here, so I'm going to divide through by PV. That will tell me how many moles are in this sample. So let's see, I think I did that upside down. So I have to divide through by RT. It should be PV over RT. Now, I didn't do that on purpose, but that is something to watch out for because that is a very common mistake that I see on exams. So be careful with your algebra when you're rearranging your equation. So R is 0.0821 liter atmospheres per Kelvin mole. Right? And again, keep those units in mind. The temperature is 30 degrees Celsius. Add 273, that would be 303 Kelvin. Right? The pressure, 745 millimeters of mercury. And we're going to have to divide by 760 to turn that into atmospheres. So 745 divided by 760 is 0.9803 atmospheres. That goes on top. And the volume, 250 milliliters, would be 0.250 liters. Right? But again, get your volume units to match the ones you get from R. Now, that will leave moles, so that will tell us how many moles are in this sample, and moles didn't change, so it'll be the same moles after the change. So that's 9.85 times 10 to the minus third moles of gas. Right now, here's where, if we remember our properties at STP, right, I'm just one step away from my answer. So take this quantity of moles, but now that the sample is at STP, there are 22.4 liters for every mole. So I multiply by 22.4. I get 0.221 liters when I round to three significant figures. Okay. Now, like I said, we could do this with our combined gas law. So we could get P1 V1 over T1 equals P2 V2 over T2, right? And you could plug all this information in, rearrange, solve for V2. You will end up with the same answer here for this particular problem. Now, there's actually a third way we could approach this problem as well. Since we do have three variables under the first set of circumstances, you could use those three variables to solve for n. And then once you know n, you also have three variables for the second set of circumstances. So you could do two consecutive PV equals nRT problems. First solve for n, then use that n along with the t and p from STP to solve for the other volume. So there's really three different ways you could go about solving that problem. But I think there is a bit of an advantage if you remember the 22.4. That gives you a little more efficient solution to that problem. So watch for that. Watch for STP to pop up here and there in problems. Okay, we'll stop the video there. We'll pick up on the next page in the next video.